All right, we're on to chapter 4, or chapter 7, section 4, and we're going to be looking at ionization energy. The ionization energy is the energy required to remove one electron from 1 mole of gaseous atoms in their ground state. So, if you have a gas phase sodium atom in its ground state, you remove 1 electron from it to get sodium ion in the gas phase. Then the delta H of that reaction is 496 kilojoules per mole. That enthalpy is the first ionization energy of sodium. So I want to compare this to neon. The first ionization energy of neon is 2,800 or 2,081 kilojoules per mole. And so that is our first ionization energy of neon. Of course, when you look at this, you say, okay, well, sodium has an atomic number of 11 and neon has an atomic number of 10. So why is it that the sodium has such a low ionization energy? And that's what we're going to answer. So if we look, why is there such a big difference in the ionization energy? Well, we'll look at the element, neon, sodium. Okay, that doesn't give us anything. Atomic number, 10 and 11, so they're very close in atomic number. Total number of electrons, 10 and 11, because they're neutral atoms here. The electron configuration, this is the first place we see something different. 1s2, 2s2, 2p6. For sodium, it's 1s2, 2s2, 2p6, 3s1. So here we've got an electron in the 3s subshell. If we look at the number of electrons in the outer shell, that number of electrons in the outer shell is 8 for neon, and it's only 1 for sodium. That also means that the effective nuclear charge felt by outer shell electrons for neon is, using our rough approximation, is approximately 8, whereas for sodium it's approximately 1. If we look at the non-bonding radius, we'll find that for neon the non-bonding radius is 0.70 angstroms, but for sodium it's much, much bigger at 1.86 angstroms. That means that that outer shell electron is much further away than the outer shell electron in neon. And then finally, when we look at the ionization energy, it's much larger for neon than it is for sodium. All right, so that is why we have such a big difference in ionization energy. All right. We want to look at the first ionization energy of each of the first 54 elements. So hydrogen is here, and then there's helium up there. And then here's lithium, and notice what happens. So lithium is over on the left side of the periodic table. I'm going to get my periodic table. So here we've done hydrogen, helium. Now we're going to do lithium and work our way across. So look at what happens as we work our way across. So there's beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Now we already know sodium is much lower when we go down to element 11. So sodium is much lower down here. And then you'll see a similar pattern as we go across the periodic table from sodium to argon. That's period 3. So we've already picked up one of our general trends. And that general trend is, as we go from left to right across the periodic table, ionization energy increases. So we will find that the ionization energy increases, again, as we go from left to right across the periodic table. All right, here from lithium to neon, it goes up. From sodium to argon, it increases. Now we're going to look at the next period. Here's potassium. Here we're going through the transition metals. We'll get something interesting happen here at the end of the transition metals. And then it continues back up as we go towards krypton. So again, the general trend is it increases as we go up and to the right, or as we go to the right. And then now I want you to look at the ionization energy of helium, neon, argon, and krypton. And you'll notice that the ionization energies decrease as we go down in that group. So we go from helium to neon to argon to krypton. So we would expect for xenon, and xenon is the one it's going to be out here, we expect it to be lower. We'll also notice that as we went down, so here's lithium, sodium, potassium. So as we're decreasing down that column, we also see that that one is decreasing. So ionization energy decreases as you go down in a column. So let's look. There's rubidium. You'll see rubidium is lower than potassium. Here as we're going across, again, we get a little hiccup there at the end of our transition metals. And then finally at xenon, we'll see that it still has a relatively high ionization energy, but not quite as high as the other noble gases. Now, if we were to go further, we would find a similar trend in later periods. All right, so those are first ionization energies. So now I'm going to show you a periodic table that's got the values on it. And with this, we'll look at the trend. And again, the general trend is that ionization energies increase as you go up and to the right towards helium. So as you go up and to the right towards helium, they increase. Okay, so given that, let's look at number 41 on the in-class assignment. So here's 41. I've got my handy-dandy periodic table there. And then there's 41. So based on their positions in the periodic table, predict which element of the following pairs will have the larger first ionization energy. So chlorine versus argon. All right, well, there's chlorine, there's argon. Argon's further to the right, so argon. See, this is an easy game. Beryllium versus calcium. Well, there's beryllium, there's calcium. Since beryllium, there's beryllium and calcium. Since beryllium is further up, we would expect beryllium to have a larger first ionization energy. Potassium versus cobalt. All right, again, here is potassium, there is cobalt. So as we go to the right, ionization energy would increase. So cobalt would have the highest not calcium, cobalt. Let's try that again. CO would have the higher first ionization energy. And then finally, sulfur versus germanium. So here's sulfur, and there is germanium. Sulfur is both above and to the right, so we would expect it to have the higher first ionization energy. So sulfur would have the higher first ionization energy. Now, sometimes people say, well, what if you've got conflicting trends? So what if instead of sulfur and germanium, we had picked silicon and selenium? And there, I would say the answer is, silicon is above, but it's further to the left. I would say the best way to approach that kind of thing is just to look it up. So when it comes to test, I'm not going to ask you a conflicting trend. I will sometimes ask you a reinforcing trend. So if it's above and to the right, then the one that is above and to the right will have the larger first ionization energy. All right, so we'll go back and we'll look at the next thing. Now, one thing, there was a discontinuity between beryllium and boron, and I'm going to go back a couple of pages and show you these discontinuities that I'm talking about. So we get this little, it's generally increasing as we go from left to right, but we get a little dip there between beryllium and boron. We also get another dip between nitrogen and oxygen. And then you'll see it again between magnesium and aluminum. And then here again between phosphorus and sulfur. Now this one's not as pronounced, but it's definitely still there. We also get these little dips, zinc and gallium, cadmium and indium. Well, we're going to find that these happen for a very logical reason, and looking at the electron configurations for each of those elements will give us a clue as to why that is the case. So here is the electron configuration for beryllium. And just so everybody knows here, come back over here, there's beryllium, element number 4. So there's only 4 electrons. So we're going to have 2 electrons in the 1s and 2 electrons in the 2s. That will give us an electron configuration of 1s2, 2s2. And then for boron, So come back over here. Here's boron, and it has an electron in the 2p subshell. So 1s, there's 2 electrons there, 2 electrons in the 2s subshell, and then we put 1 additional electron into the 2p subshell. And so that electron configuration is going to be 1s2, 2s2, 2p1. Well, this explains why boron has a lower first ionization energy. We have 1 single electron in the 2p subshell, and that 2p subshell is higher in energy than a 2s subshell. So it will be just a little bit easier to remove this 2p electron than it will be to remove the 2s electron in beryllium. And that's why we have that little dip. In between boron and beryllium. So the ionization energy for boron is a little bit lower. Now, as a similar kind of problem, we saw that between nitrogen and oxygen, we also had a discontinuity. So the electron configuration for nitrogen, and again here we'll come over here, nitrogen has 7 electrons. So 7 electrons, we'll get 2 here in the 1s, 2 in the 2p, and then we'll put 3 into the 2p subshell. So 1s2, 2s2, 2p, 3. For oxygen, our electron configuration, again, I'm going to come back over here. There's oxygen, element 8. So there's 8 electrons. So we'll have 2 there, and we need to put 4 into the 2p subshell. All right, so now that we put 4 of those electrons into the 2p subshell, 1s2, 2s2, 2p4. All right, so now that we've done that, we can see that in the nitrogen, we have a halfway filled subshell. The 2p subshell is halfway filled. And in oxygen, the 2p subshell is more than halfway filled. We've got that additional electron. So by removing, it's going to be a little bit easier to remove that electron because, one, there are repulsive forces between that electron and the other electron in that orbital. And so because of those repulsive forces, it'll be just a little bit easier to remove that. And you recall that we seem to have greater stability, lower energy, when we have a halfway filled subshell than when we have a partially filled subshell. So this explains why oxygen is a little bit lower ionization energy than nitrogen. So now we want to look at the second ionization energies. So the ionization energy, again, it's the energy required to remove 1 electron from 1 mole of gaseous atoms in the ground state. That's the same definition that we saw a little bit ago. This is the same one. Sodium has an ionization energy of 496 kilojoules per mole, whereas sodium plus 1, if we ionize it and get sodium 2 plus, we will end up with an ionization energy of 4,562. Well, that is the second ionization energy of sodium. Now, you would expect that the second ionization energy is always going to be larger than the first ionization energy. Recall, as soon as you take 1 electron away from an atom, all the remaining electrons have fewer repulsions, so they get closer to the nucleus. So once they get closer to the nucleus, that means any subsequent electrons are going to be more difficult to remove. That's perfectly normal. However, when we look at this, we'll see that that's a huge change in the ionization energy. It's not just twice as big or somewhat bigger. It's almost 10 times as big. It's an order of magnitude difference. Well, the reason for that is because of the electron configuration. All right, so it's because of that electron configuration. So I just real briefly, I don't have this typed out, but let's go over and look at this. So for sodium, we've got an electron configuration of 1s2, 2s2, 2p6, 3s1. And if we remove 1 electron from that, we'll have sodium plus 1. Its electron configuration will be 1s2, 2s2, 2p6. So it's fairly easy to remove an electron from the 3s subshell, but it's going to be much more difficult to remove an electron from the 2p subshell, because those electrons are much closer to the nucleus. And on top of that, we've already removed an electron, so they got even closer than they were before. And that's the rationale. When you run out of electrons in the outer shell, it becomes much more difficult to remove the next electron. So if you think about all the times that we have seen sodium 2+ in this textbook, well, this would be the first time. We just don't see sodium 2+, and the reason is it's too unstable. All right, so it requires more energy to remove each successive electron. All right, we already know that. So if you just come down here and pick, let's say, aluminum. Aluminum, the first ionization energy is 578. The second one, 1817. And then the third one, 2745. So it does get more difficult to remove subsequent electrons from that atom. However, when all of the valence electrons have been removed, it takes a great deal more energy, usually on the order of 3 to 10 times as much energy as the previous one. So you'll see that the third electron in aluminum was 2745, but to remove a fourth electron, we would have to remove it from the 2p subshell. So here's aluminum. We took our first one from 3p. That was relatively easy. The next two came from the 3s subshell. All right, so those two from the 3s subshell. But then this fourth one, this 11,577, that one came from the 2p subshell. And as we already know, that is much more difficult. It's much more difficult to remove that. All right, and then here I've got a graphic. It's a graph that shows the first 5 ionization energies of the first 54 elements. Now, I don't have them labeled, but it's pretty straightforward. The first ionization energy is this one down here. This is the same graph that I showed you guys earlier when it was the first ionization energy, except all the other ones are so much bigger, we had to kind of stretch it out. The orange one is the second ionization energy. This gray one is the third. The yellow one is the fourth, and this light blue one is the fifth. So even if you're having trouble seeing the colors on your screen, just keep in mind that they are in order. So first, second, third, fourth, and fifth. Now, a couple of things you'll notice here. Helium or hydrogen only has one ionization energy, and that's because it only has one electron. Once you remove one electron from it, you can't remove another electron. There's no more electrons to remove, so that's why we only see one. For helium, we only have 2. For lithium, 3. Okay, so there's that. Now, the other thing that I wanted to point out is that you can see this phenomena that I showed you on this previous slide, right, where you see a big jump in the ionization energy. So here, this one, for example, was for aluminum. And we'll look at, let's look at silicon. We're going to look at silicon. So silicon is element number 14. So here is element number 14. Silicon, just as a reminder, silicon is element 14. It's in group 4. That means that there are 4 valence electrons in silicon. You'll see that here's the first, the second, the third, and the fourth. They're all pretty close to each other. I mean, they're getting kind of big, but they're still pretty close to each other. But then the fifth ionization energy is huge. So there's a big jump between the fourth ionization energy and the fifth ionization energy. So I want you to be able to recognize numbers like we saw here on this previous page and tell me what group an element is in just based on the ionization energies. So look for that big jump between one ionization energy and the next ionization energy. All right, let's look at 36 and 37 on the in-class assignment. All right, so number 36. write the equations that show the process for the first two ionization energies of tin. All right, so tin is Sn, and it does have to be in the gas phase, and it becomes Sn plus gas plus an electron. Now, I don't know the delta H of that process, but we're going to look that up here in just a moment. And then we'll look up Sn gas going to Sn2 plus gas plus an electron. And then we will figure out what the delta H is. I'm going to look that up on a website that I call Web Elements. I've shown that to you before. We'll go back over here. All right, so here is the Web Elements. And I've already got tin pulled up, and this has got the ionization energy. So here you will see those numbers. I'm just going to write down these numbers. These are always going to be positive numbers. So ionization energies are always positive. So that one is positive 708.58. Probably don't need the 0.58, but that's kilojoules per mole. And then 1411.88. So 1411.88 kilojoules per mole. All right. All right, so now we want to do the fourth ionization energy of titanium. We're not doing the first three, we're just doing the fourth. All right, titanium is Ti. And if it's the fourth, then we're going to be starting with 3 plus. And we'll be going to Ti4 plus an electron. All right, and then we are going to look up that ionization energy. I'll go back over here. So this is still 10. Let me scroll down here. Titanium is right there. This website's kind of cool because it also gives you electron configurations. If you got stuck on any stuff there, you can do the electron configurations. All right, so the fourth ionization energy, there it is, 4174.65. So 4174.65 kilojoules per mole. All right, so now that we've done those, let's look at 37. All right, why are ionization energies always positive quantities? Well, the reason for this is that you always have to add energy to remove an electron. If an electron is attracted to an atom, then you have to add energy to take it away. So, and since you're always having to add energy, then that means that you're going to have positive ionization energies. All right, why does fluorine have a larger first ionization energy than oxygen? So fluorine versus oxygen. Well, we'll see that fluorine is further to the right than the oxygen, and so we could just say, oh, because it's further to the right. However, probably the best way to think about this is fluorine has an effective nuclear charge of about 7, because it's in group 7, whereas oxygen has an effective nuclear charge for its outer shell electrons of about 6. So because of the greater effective nuclear charge, the electrons in the outer shell of fluorine are held more tightly. They're held more closely to the nucleus. And so that's why it has a larger first ionization energy. So fluorine. Z effective than oxygen. And again, because it has a larger Z effective, that pulls on the electrons more tightly, holds them more closely to the nucleus, and therefore it will be more difficult to remove it from fluorine than from oxygen. All right, why is the second ionization energy of an atom always greater than its first ionization energy? Well, we talked about this, but let's go ahead and say it again. Whenever we remove one electron from an atom, all the remaining electrons have fewer repulsions, and so they get closer to the nucleus. And that makes it more difficult to remove any subsequent electrons. All right, I'm going to read that again because my handwriting is a little messy here. So whenever you remove an electron from an atom, all the remaining electrons get closer to the nucleus, making it more difficult to remove the subsequent electrons. Okay. So next we want to look at the electron configurations of ions. So for cations, when we remove electrons from cations, we're usually going to lose them from the highest energy level. And that's even though sometimes we don't add them in the same order, we always remove them from the highest energy level. So just as an example, this one is really easy. From lithium, we have 1s2, 2s1. We always remove one electron from lithium when we make the lithium ion. And so the electron configuration, or that electron, is going to come from the 2s level, and we're going to be left with just 1s2 as our electron configuration for lithium ion. For other ones, it's a little bit more complicated, but it's not too bad. So for iron, when we form a +2 charge on iron, so iron 2, here is our electron configuration for the element: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Well, again, even though we filled in the 3d subshell last, we're actually going to remove the electrons from the 4s level. So when we remove 2 electrons, we will lose 2 electrons from the 4s subshell. And we will get for iron 2, 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. When it comes to anions, the electron configuration is going to be filled out until you fill the outer orbital, or the outer shell. So typically that's going to get to 8. We actually call this the octet rule, and we're going to talk about the octet rule in chapter 8, so you got that to look forward to. So for fluorine, as an example, the electron configuration is 1s2, 2s2, 2p5. Well, typically it will pick up an electron and become fluoride, and it'll become 1s2, 2s2, 2p6. We'll have 8 in its outer shell. Again, octet rule. We'll talk about that more later. So we got 1 extra electron in that 2p subshell. So let's look at 7.43 and 7.46. So here is 7.43. And I think on this one, it is beneficial to write down what the electron configuration is of the neutral atom and then look at what we would take away. So for just silicon, our electron configuration is 1s2, 2s2. There's 14 electrons, by the way, here. So for silicon, there's 14. So 1s2, 2s2, 2p6, 3s2, 3p2. And then when we look at that, where are we going to take 2 electrons away from? Well, we'll take them from the 2p subshell. If you have both to pick from, you'll take it from the one that is higher in energy, and the p subshell is higher. So Si2 plus is going to have the electron configuration 1s2, 2s2, 2p6, 3s2. All right, for bismuth. Now for bismuth, bismuth is way down here on the periodic table. I'm not going to write out every single one. I'm going to use the condensed formula. So we're going to do xenon 6s2, 4f14, 5d10, and then 6p3. All right, so for bismuth, again, that's going to be xenon, and then 6s2, 4f14, not 114, just 14. So 4f14, 5d10, 6p3. Now, when you're looking at this, you're looking at that electron configuration, you say, well, how do you remember how to do this? Well, I remember because I've done this many, many times. But if you go back to that pyramid in chapter 6 that I showed you, you can usually pick up, as long as you know that xenon here this is in period 5, so this would be the 5p subshell, and so you just pick up after that 5p, and you'd be able to do your electron configuration for the rest of it. All right, in fact, I just decided I'm going to show you guys that that pyramid just so you remember what I'm talking about. So again, xenon is in period 5 of the periodic table. And so that means this is 5p6. All right, so now I'm going to come back over here. And so here's 5p. So we had done 4d. 5p. Yes, so there's 5p. And then after 5p, there's 6s, 4f, 5d, and 6p. All right, so if you do that, so 6p, 4f, 4d, and then 6p. 6s, rather, 4f, 5d, and then 6p. All right. I just want you guys to realize that that's how that is. Now, we have a +3 charge on bismuth, and when we're removing it, we're going to take it from that 6p subshell. So for bismuth, we'll have Bi3+, and it will be xenon 6s2, 4f14, 5d10. Now, it's not uncommon when people are writing out electron configurations to rewrite it so that they are in order of their principal quantum level. So they'll group all the 4s, 5s, and 6s together. But again, that is not necessary. You can just put them in the order that you filled them. All right, next we've got tellurium, Te2-, that's actually telluride. So tellurium has 52 electrons. We're going to write the electron configuration of just tellurium by itself. And that electron configuration is krypton, so Kr. And here it is Kr, that's 4p. And then we'll have 5s, 4d, and then 5p. So 5s2, 4d, 5d10 5p4. When we add 2 electrons, we're going to add those 2 electrons to the p subshell, that 5p subshell. So for telluride, Te2 minus, it will be krypton 5s2 4d10 5p6. All right, so now for aluminum. Aluminum, the electron configuration is 1s2. There's 13 total electrons here, so we'll do 1s2, 2s2, 2p6, 3s2, 3p1. When we remove 3 electrons, they're going to come from the outer shell, from the 3s and 3p subshells. And so aluminum 3 plus is going to have the electron configuration 1s2, 2s2, 2p6. And we will find it will be isoelectronic with neon. All right, now for mercury 2. So mercury has a lot of electrons, so we are going to use the condensed formula starting with xenon. And so just kind of like what we did up here. So for Hg, just elemental mercury, we've got xenon 6s2 4f14 5d10. So 54 plus 2 is 56, plus 14 gives us 70, 80 electrons. So that is correct there. So that gives us the 80 electrons that mercury has. So now when we look at this, if we remove 2 electrons, we need to take them from the highest principal quantum level. So we're going to take them from level 6. So Hg2 plus is going to have the electron configuration of xenon 4f14 5d10. So we will take them from the 6s level. Finally, let's look at nickel. So again, we'll start with the electron configuration for nickel by itself. So for nickel, we've got, let's see, where is nickel there? So it's number 28. So we can do argon. Argon is 18, and we need 10 more. So 4s2, and then 1, 2, 3, 4, 5, 6, 7, 8. So 4s2, 3d8. So that's the electron configuration of just nickel. And then the electron configuration of nickel 2 is going to be argon. And we will take those electrons from the 4s subshell, so we will just get 3d8. And that will be the correct electron configuration for that. All right, so we also want to do number 46. I'm just checking on that. Identify the element whose ions have the following electron configuration. This is actually a little bit easier than trying to write out the electron configuration, because here you just have to count the number of electrons and then figure out which element it is. So it's a 2 plus ion, and it's argon 3d9. So we come back over here, and we've got argon has 18, and then 3d9, 9 plus 18, gives us 27 electrons. Well, it's a +2 charge. That means that the neutral atom had 2 more electrons. So our atomic number, Z, is 29. And element 29, as we can see, is copper. So that is going to be copper 2 plus. So again, we had 27 electrons. It was a +2 ion, so that means that we had taken 2 electrons away. So we're going to add 2 to that to give us our atomic number, which was 29, and it was +2 charge, so we'll put copper 2 plus is the ion. All right, next we've got a 1 plus ion that is xenon 4F14, 5D10, 6S2. You'll see here that it has written these in the order, not in the order that you fill them, but in increasing principal quantum level. All right, so let's count up the number of electrons. Xenon is 54, and then 54 plus 14 gives us 68, plus 10 more gives us 78, plus 2 more gives us 80. So there are 80 electrons. Since there's one electron that has been removed, that means our atomic number is 81. So if we come back over here, element 81 is thallium. And in case you're wondering, thallium is not something you want to mess with. It is dreadfully poisonous. If you were to consume a small amount of thallium, it would kill you, but it wouldn't do it quickly. You would die like 3 weeks later. So don't mess with thallium. All right, and don't get any ideas. If you poison somebody with thallium, you are going to get caught. So don't do that either. All right, so tips on not murdering people. Okay, so now it says how many unpaired electrons does each contain? Well, we'll see here in 3d9. So if we draw the d orbitals, 1, 2, 3, 4, 5. So this is the 3d subshell. If there's 9 electrons there, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. That means we've got 1 electron that is unpaired. So copper 2 has 1 unpaired electron. And then for thallium 1, if we look, the 4F14, that's full. 5D10, that's full. 6S2, that's full. So thallium plus 1 has 0 unpaired electrons. Okay. So next, we want to look at the concept of electron affinity. So electron affinity is kind of like the opposite of ionization energy. Electron affinity is the energy released when one electron is added to 1 mole of gaseous atoms in their ground state. So chlorine, if you have a chlorine atom in its gas phase and you add an electron to it and you get chloride ion in the gas phase is important here. It's going to have a delta H of negative 349 kilojoules per mole. That happens to be the largest negative electron affinity value of all the elements. So this is the electron affinity of chlorine. Here's oxygen. Again, it has to be an atom. So an oxygen atom plus an electron gives you O minus in the gas phase. And delta H there is negative 141 kilojoules per mole. And so the electron affinity of oxygen is that negative 141. So these numbers just by themselves don't mean a whole lot until you look at them together. And so here, these are the electron affinities for many of the main group elements. So the electron affinities for many of the main group elements. Within a group, the electron affinities typically don't change very much. You'll see that going from top to bottom within any group, that they're pretty uniform. From one group to another, the changes are a little bit bigger, and they can be a little bit more confusing, but they're easily explained. The general trend, if you'll notice, the one that has the largest negative, so the highest magnitude, is 7A. And then if you look, the next one is 6A. And the next after that is going to be 4A. All right, so all of the ones in 4A are bigger than the ones in 5A. And then we'll say 5A. So 7A, 6A, 4A, 5A. And then I just say the rest, because these electron affinities are pretty small, although there's something interesting that happens here between 2A and 3A. And I'll talk about that here in just a second. But in general, what we can say is that that the electron affinity is the largest magnitude for 7A, then 6A, then 4A, then 5A, and then the rest, the other groups. And if you're going to memorize something, and this is what I would encourage you to memorize, 7A greater than 6A, greater than 4A, greater than 5A, greater than the rest. I am not going to make you distinguish between one that's up on the top and one that's on the bottom. So I won't have you say which one's bigger, fluorine or chlorine. You know, it's chlorine, but I don't expect you to memorize that because there's not a clear trend. It mostly increases as you go up unless it doesn't, and that's not a very clear trend. You'll notice that some of these have positive values, so greater than 0. That means that you cannot measure the electron affinity for things that are positive. That is simply because thermodynamically it's just not possible to make those endothermic measurements with those things. So we'll see these greater than 0. It just means it can't be measured. Now, there are a couple of discontinuities that we see, and it's just like what we saw for ionization energy. The difference here is that we're adding electrons instead of removing electrons. And so here in 2A, we already have a full S subshell. And so adding another one is not very easy. We would have to add it to the P level. Likewise, when we get halfway full on our P subshell, like we do for nitrogen, adding another one, it would have to share an electron. Remember, thanks to Hund's rule, remember the bus, we would have to share an orbital. One of those electrons would have to share an orbital. And so it's a little bit more difficult to add an electron to our group 5 elements. But all that said, this is our pattern. I want you to remember this order. All right, so for our next section, we're going to look at metals, nonmetals, and metalloids. And we want to think of this in terms of how much metallic property do these things have. Now, I'm going to show you this exact same picture here a little bit later, but you can see the trend, increasing metallic character as you go to the left and as you go down. We'll see that all of these elements that are kind of this beige color are metals. And over here, the green ones are nonmetals, and then the purple ones are metalloids. And hydrogen is kind of its own thing. It is definitely a nonmetal, so that's worth remembering. We're going to find that metallic character increases as we go to the left and as we go down. And if you think, well, what do we mean by metallic character? Well, all of the things you think of when you think of a metal. Metals are shiny, they're usually solid, they're good conductors of heat and electricity. Those kinds of things, they increase as we go to the left and down. So metals, they definitely differ from nonmetals, and we'll look at the different ways that they differ. Metals tend to form cations, and nonmetals tend to form anions. And so these are some of the common cations that we form with our metals, and so you'll see there are a bunch of them here. This is by no means all of the possible cations. There are some extra possibilities, like for nickel here. I know you can get nickel 3, not very easily, but you can get nickel 3. Chromium, there's a couple of possibilities there. So this doesn't show everything, but it does show quite a few of our oxidation states. All right, so there's those. And you'll notice that all the metals form cations, even the ones that are over here in the P block, they tend to form cations. Even polonium here, if you were unlucky enough to get some polonium, you'd be worse off than if you got the thallium. It's even more poisonous. But the polonium here, even it forms cations. All right, and then you'll see that the nonmetals tend to form anions. If they're monatomic, they tend to form anions. And sometimes they'll form oxyanions as well. So they will form the anions. Noble gases tend not to form ions at all. So metalloids tend not to form ions. They tend to form molecular compounds. So we'll see covalent bonds with most metalloids. You'll also see beryllium here. Beryllium's just not very good at forming the +2 cation. So most of the time, it will form a covalent bond. And we'll talk about that a little bit later. So properties of metals versus nonmetals. When you think about all the things that you know about metals, metals are typically shiny. They have luster is the term we like to use. They are usually good conductors of heat and electricity. They are malleable and ductile. Malleable means you can pound them into sheets. Ductile means you can draw them into wires, which is why we can have stuff like copper wire. Solids at room temperature, with the sole exception of mercury, although there's a couple that are kind of close. They have low ionization energies. So low ionization energies, small electron affinities, and they typically will form cations pretty easily. All right, so metals tend to form ionic compounds. And the oxides of metals tend to be basic. And I'm going to show you some pictures of that here in just a few minutes. For nonmetals, the properties are almost exactly the opposite. Whereas metals are shiny, nonmetals, if they're solids, they tend to be dull. Now, that's not always the case. Iodine has a little bit of a shiny character to it, but they tend to be dull. Whereas metals are good conductors of heat and electricity, nonmetals are typically poor conductors. Metals are malleable and ductile. If you have solid nonmetals, they tend to be brittle. Metals are solids at room temperature. Well, nonmetals are kind of all over the place. Some are solids, some are liquids, and some are gases. There's only 2 liquids on the periodic table. One's a metal and one's a nonmetal. So that, liquids, we don't have much of a distinction there. But nonmetals, typically we get both, are both solids, liquids, and gases, all 3 of those. Metals tend to have low ionization energies, whereas nonmetals tend to have fairly high ionization energies. Small electron affinities for the metals, and by that I mean small magnitude because they're negative, right? And the nonmetals have large negative electron affinities. Now, that's not universally true, but if you look at the halogens, that's definitely true. Metals tend to form cations. The nonmetals tend to form anions fairly easily. Metals tend to form ionic compounds. Nonmetals will form both ionic and covalent compounds. If you've got a metal, and a nonmetal, it's probably an ionic compound. If you just have nonmetals, it's probably a molecular compound that only has covalent bonds. Metal oxides tend to be basic. Well, nonmetal oxides tend to be acidic. And I'm going to show you something about that here in just a moment. So metal oxides tend to be basic, and in fact, they get more basic as you go further to the left and down on the periodic table. So compounds between metals and nonmetals tend to be ionic. I think we already said that. Metal oxides tend to be basic, and they will react with acids. So here is a picture, and we've got the nonmetal, or the metal oxide, nickel 2 oxide. And then on the left side here, we've got some nitric acid, and on the right side, we just have regular water. If you take some of that nickel 2 oxide and drop it into the nitric acid, it will react to give you nickel 2 nitrate in solution. So it will dissolve. So the acid will react with the oxide to give you water. If, on the other hand, you take that nickel 2 oxide and you put it into water, it doesn't dissolve. Hardly anything happens. It will make it a little bit more basic, but it is not going to dissolve very easily. So we won't really get anything to dissolve. This is true for the vast majority of oxides. The only exception on these metal oxides, the only exception are your group 1 oxides and the bottom of group 2, calcium, strontium, and barium. Those oxides, when you put them into water, they will form the metal hydroxides, and those are strong bases, and so those will dissolve. But all the other ones, you're going to get an insoluble ionic compound. Nonmetal oxides tend to be acidic, and as you go further to the right and up, those nonmetal oxides tend to be even more acidic. So nonmetal oxides over here tend to be pretty darn acidic. So we'll come back over here. All right, so substances containing only nonmetals tend to be molecular compounds. That's true. But here we go. Nonmetal oxide, or most nonmetal oxides are acidic. And then here is an example. This is dry ice. And dry ice, as you guys are familiar with, that's carbon dioxide. Carbon dioxide, when you put it into water, it will react with the water to give you carbonic acid. So it will become acidic. Here we've got the indicator bromothymol blue, and it looks like bromothymol blue, if the pH is right at 7, bromothymol blue is kind of a green color. So it looks like somebody, when they set this up, they made this a little bit basic. It makes it prettier if you make it all blue to start with. Well, as the carbon dioxide, the dry ice, starts to bubble in the water and you get more of that carbonic acid, the pH of this will go down fairly quickly and it will turn to a yellow color. So you will get this sort of yellow, and if it gets really low, it'll almost go colorless. So, and like I said, if the pH is right at 7, you should see a green color. But it looks like somebody messed with it a little bit to make it a little bit basic because, you know, everybody loves their alkaline water, right? All right, so let's look at 7.60 on the in-class assignment. All right, and we want to arrange the following oxides in order of increasing acidity. All right, again, metal oxides get more basic as you go to the left and down. So like these are really basic over here. These are not quite as basic, and things get more acidic as you go to the right. So we have really basic and we get more acidic. So really we just have to look at what group each of these is in. So carbon's in group 4, calcium's in group 2, aluminum is in group 3, sulfur is in group 6, silicon is in group 4, and phosphorus is in group 5. So that means that our most basic, our least acidic, if you want to think of it that way, is going to be group 2, calcium oxide. So that one's in group 2. Next, we've got the group 3 of aluminum oxide. So I'll put Al2O3. That one's group 3. We've got 2 that are here in group 4. So carbon dioxide and silicon dioxide. And we'll find that they tend to get more acidic as you go up. So carbon dioxide is going to be more acidic than silicon dioxide. So we'll put SiO2 and CO2. And then group 5, we've got P2O5. So P2O5 is that. And then let's see. We've got sulfur trioxide, and so sulfur trioxide is going to be the most acidic there. All right, now if you add water to each of these things, you're going to get either a base or an acid, and I'm going to go ahead and tell you, even though this question is not specifically asking you this, I'm going to go ahead and tell you what you'll get. If you add calcium oxide to water, you'll get calcium hydroxide, so CaOH2. Aluminum oxide, you will get H3AlO3. And is it an acid? Is it a base? Well, it is what it is. It is H3AlO3. H3, I'm making sure I got that right. That is correct. That is correct. You'll take 2 of these and 3 water molecules, and you'll get that. All right, silicon dioxide, it just doesn't react. Silicon dioxide is sand or quartz, and if you put sand or quartz in water, you'll have wet sand. It doesn't react. Carbon dioxide will react, and you'll get H2CO3, which is carbonic acid, and that is a little bit acidic. P2O5, you'll get H3PO4, phosphoric acid. And for SO3, you will get H2SO4, which is sulfuric acid. So if you take water and you bubble sulfuric acid through it, or bubble SO3 through it, you will get sulfuric acid. Kind of cool. All right. Now, I mentioned this, and one thing that you will notice is that the oxidation state of the thing that isn't oxygen remains the same. So the oxidation state of calcium is 2, aluminum is 3, silicon, well, it didn't change, but it's 4, carbon is 4, the oxidation state of phosphorus is 5, and the oxidation state of sulfur is 6. I just mentioned that, and we're going to see some reactions a little bit later as well. Okay, so we're almost done. Even though we're at an hour, I'm going to keep going, and we're going to finish this chapter. All right, so we looked at the properties of metals. Metals are shiny, good conductors, that kind of stuff, and nonmetals are dull and poor conductors and that kind of thing. Well, metalloids, it's complicated. Usually the properties are just kind of in between. So if you were to look up the relationship status of metalloids, it's complicated. Metalloids tend to have characteristics of metals and nonmetals. So some of the characteristics. So as an example, silicon. So here is a sample of silicon. And you'll notice the silicon, it looks kind of shiny. So it looks kind of like a metal. So if you were to look and try to measure the conductivity, it's considered a semiconductor. It's not a great conductor, but it's not a good insulator either. And so it is a semiconductor. And in fact, if you add impurities, you can specifically make it conduct the way you want it to. All right. We will find that silicon is shiny like a metal. And so you see it shiny, but it's also brittle like a nonmetal. So it's definitely not malleable and ductile. You can't bend silicon to make it, into a particular shape. It forms oxides that are neither acidic or basic. So you'll find that they are not acidic and not basic. All right, and then back to this metallic character. So all these properties that we've talked about metals, those properties increase as we go down into the left over here towards cesium. I'm going to leave francium out of this because francium's so radioactive. It's gonna make you have a bad day if you get exposed to francium. All right. So here we'll switch over. How are metallic character and first ionization energy related? Well, metallic character increases as you go down into the left towards cesium. So metallic character increases going this way. Ionization energy increases as you go up and to the right towards helium. So they are opposite. So metallic character All right, so again, metallic character increases as you go down into the left. So down into the left increases, and then ionization energy increases as you go up into the right. So they are opposite. I'm not going to say that they are inverse relationship, even though they are opposite, because inverse has a mathematical meaning that's not quite true for those two things. All right, so on number 57, we want to predict whether each of the following oxides is ionic or molecular. Explain the reason for your choices. So here's the thing. If you've got a metal and a nonmetal, it should be ionic. If you have a nonmetal with another nonmetal or a metalloid with a nonmetal, it's probably molecular. And that's pretty much it. So S and sulfur and oxygen are both nonmetals. This should be molecular. Not only should it be, it actually is. MgO, that's a metal and a nonmetal. That should be ionic. I put too many I's in there. Let's try that again. Ionic. Lithium is a metal. Oxygen is a nonmetal. That should be ionic. Phosphorus, nonmetal. Oxygen, nonmetal. That should be molecular. Yttrium is a metal. Oxygen is a nonmetal. So that should be ionic. And then nitrogen, N2O, nonmetal, that should be molecular. All right, so our last thing that we're going to look at in chapter 7 is there's a couple of sections here, and we're just going to kind of go through the different groups and the different categories and talk about some of their properties. So let's look at the trends for the group 1A alkali metals. So they are soft metallic solids. Here is a chunk of sodium, at least I'm pretty sure it's sodium. Sodium, and we've got a metal, and you see he's wearing gloves because sodium tends to react with water, and so you wouldn't want to touch it directly with your hands, but you can cut through the sodium with a knife, and it's not even very hard to do. You could cut through it with a dull knife if you wanted, although a sharp knife is going to be a little bit better. I've used scissors to cut sodium before. Okay, they are found only in compounds in nature and not in their elemental forms. So, like if you were to go to where you had a sodium-rich deposit, like a salt mine, you would not find elemental sodium ever. And it's just because it's so reactive. Compounds for our group 1 metals tend to be water-soluble salts. If you remember our solubility rules, group 1A containing salts tend to be soluble. And typically, they have typical metallic character. They have luster and conductivity. Here, this metal doesn't look like it is very shiny, and that's because as soon as you cut it, it reacts very quickly with the oxygen in the air. So it tends to get kind of an ashy gray color to it. But if you cut it and look at it right away, it's shiny. And excellent conductivity properties. Liquid sodium is often used as a conductor in certain types of nuclear reactors. It's just incredibly good conductor of electricity. So, all right, and as I mentioned, they are very reactive, so you don't want to get water on your metals, unless that's, of course, your goal is to show how they are reactive. So alkali metals, they have very low densities and low melting points. So here are electron configurations. We've already looked at those. Notice the melting points are quite low, and in fact, cesium has a melting point of 28 degrees Celsius. If room temperature, instead of being 25 or 30, then cesium would count as a liquid at room temperature. But it is a solid according to our measurement. We have room temperature of 25 degrees Celsius. The densities here are very low. In fact, all these these first three densities are less dense than water. So we don't think of metals typically floating on water, but if you take sodium and drop it into water, it will float. Well, it'll react violently with the water, but it will float while it's doing so. All right, radius are given there, but here are the ionization energies, and these low ionization energies are what make them so reactive. So the low ionization energies, and they get more reactive as you go down the group, and that's because as you go down in that group, you will find the ionization energy gets lower. Alkali metal reactivity, quite famously, they will react with water. But it gets more reactive as you go down. If you drop lithium into water, it will bubble vigorously, and so you'll get hydrogen gas coming off vigorously. If you drop sodium into water, it comes off vigorously, but it's a little exothermic and often will catch the hydrogen on fire, which is very exciting. Potassium, you drop it in water and it kind of explodes. Very exciting. So very exciting. All right. Alkali metal reactivity with oxygen. This is kind of interesting. Lithium reacts with oxygen to make an oxide, just regular oxide. That's exactly what you would expect for most metals. It would just form a regular oxide. Sodium, if you leave sodium out, it will react with oxygen to form a peroxide, sodium peroxide. And so you can reduce that and get sodium oxide if you want, but that is sodium peroxide. That's kind of interesting. potassium, rubidium, and cesium, if they're left exposed to oxygen, they will form superoxides. And this is a very unusual oxidation state for oxygen. The oxidation state for oxygen in a superoxide is -1/2. So the potassium has a +1 charge, and the superoxide has a -1 charge, and the average charge on each oxygen is -1/2. Kind of interesting. And so that is kind of a unique property. It's difficult to form superoxides with other elements. I don't know of any other ways to do it. All right, the alkali metal flame test. If you take alkali metals and you put them into a flame, and it doesn't have to be pure metal, you can use the compounds, you will get some very bright colors. Lithium, for example, gives you a nice bright red color. Sodium gives you a nice yellow color, and potassium gives you kind of a lilac violet color. These kinds of things are often used in fireworks to make the fireworks glow brightly. So when you heat, when you burn the stuff that's in the fireworks and you heat up these compounds that contain these metals, you will get these colors. So pretty cool stuff. These colors are caused by the electronic transitions that we see in chapter 6. Now, I will say that that other metals also have interesting colors when you heat them up. Copper, by the way, it gives kind of a bluish green color. Very cool looking. But again, this is caused by the electronic transitions. So the electron gets promoted up to a new level, so from like 3s to 3p, and then when it drops back down, it gives off light. And so you can take advantage of that for sodium by having sodium lamps. Now, sodium lamps aren't used as much as they used to be, but sodium lamps for much of the 20th century were very energy efficient ways to light cities, streets and cities, because it gives off a very prominent yellow color in the emission spectrum. All right, alkaline earth metals, group 2. So alkaline earth metals are a lot like the alkali metals, only less so. They have low densities and low melting points, but they're not quite as low as the densities and melting points for the alkali metals. So remember, the densities for the alkali metals were all pretty close to 1, and you'll see that these are somewhat higher. The melting points are definitely higher for our group 2 metals. The ionization energies are low, but they're not quite as low as they were for group 1. So really, the alkaline earth metals are kind of like group 1 wannabes. They're reactive, but they're not quite as reactive as the alkali metals. And I'll show you that here in just a second. And they almost always, in fact, I don't know of other situations where they don't form a +2 cation, but they will form a +2 cation after losing 2 valence electrons. So they'll lose their S subshell electrons. So alkali metal reactivity, it increases as you go down in the column, just like it does in group 1. Beryllium doesn't really react with water. If you drop beryllium in water, it just kind of sits there. If you put magnesium in water, it doesn't really react, but if you have steam, if you have, hot steam that flows over the magnesium, it will react. And then calcium, strontium, and barium, the bottom 3 in group 2. And again, here I'm going to show you the periodic table. So beryllium doesn't react with water, magnesium reacts with steam, and then calcium, strontium, and barium will react pretty vigorously with water. So the reactivity does increase as you go down in that group. And again, that's due to the low ionization energies as you go down in the group. So ionization energies decrease when you go down in any group. So now we want to look at trends for some selected nonmetals, and we're going to start with hydrogen. Hydrogen has the electron configuration 1s1, and so with s1 you might think, well, should it fit into the alkali metals? And the answer is probably not, because it doesn't really have the properties of a metal. It's not a good conductor. It's not a solid. It's not malleable and ductile. So all the things we think of, it's not shiny. So all the things we think of when we think of hydrogen don't really fit. It's just not dense enough to do that. So we don't put it in there. It's kind of its own thing. A lot of times when you see periodic tables, you'll even see that the hydrogen is separated a little bit. Now, I don't do that on my version of the periodic table. I keep it attached. But sometimes it's kind of floating up there, kind of like it doesn't fit. Hydrogen can form acids, like in hydrochloric acid, and those will dissociate in water to give H+. And if you have a hydrogen that bonds with a metal, it typically forms a hydride where the hydrogen has a -1 charge. And this is kind of interesting. 90% of the known particles in the observable universe are hydrogen. And that makes up about 74% of the mass of the known particles in the observable universe. Now, you notice I'm kind of saying of the known particles. There's all kinds of unknown particles like dark matter and dark energy, and those things I'm not including. So, but normal mass, most of it is hydrogen. And so that 74%, about 24% of the other stuff is helium. So all the other stuff like carbon and nitrogen and oxygen and iron and all the stuff that makes up you, but that's in the 2%. You are the 2%. I just thought I'd mention that. All right, group 6, the chalcogens. Chalcogens are group 6. Oxygen, sulfur, and selenium are nonmetals. Tellurium counts as a metalloid, and the radioactive element polonium counts as a metal. So, there's quite a range of possibilities for group 6. Oxygen tends to form a -2 monatomic anions, but it also can form, as we saw a little bit earlier, peroxides and superoxides, so that's a possibility. And then the other elements have many oxidation states. So sulfur and selenium and tellurium, they tend to have lots of other oxidation states. Polonium tends to form cations, which is kind of interesting. So here, the electron configurations, again, 6 valence electrons. We have a gas, and then the rest are solids. Densities are kind of all over the place. And then those are atomic radii, not very interesting. The ionization energies are fairly high, particularly among these higher ones. Polonium, it's a low enough ionization energy that you can get cations with polonium. But I will warn you about polonium. It's radioactive and deadly poisonous on top of the radioactivity. Polonium, if you want to have an interesting read, go to Google and search polonium poisoning. And you will read a story about Alexander Litvinenko and how he was poisoned by the Russian government. It sounds like a repeating pattern of people getting poisoned by the Russian government. I probably shouldn't say anything if I don't want to be poisoned by the Russian government. Please don't poison me. Okay. Oxygen has 2 allotropes, and those are just 2 elemental forms of oxygen. One is O2. That's the stuff we breathe. That makes up about 21% of the Earth's atmosphere. So that's O2. And then ozone is stuff we don't want to breathe, at least not in any significant amount. We do want it in the upper atmosphere, but we don't want it down at ground level because it is a known carcinogen when you breathe it. But it's good to have it in the upper atmosphere. Group 7, the halogens. And so for the halogens, fluorine, chlorine, bromine, and iodine, they have 7 valence electrons. These are just typical nonmetals. These are all going to be nonmetals, and they're very typical. They have highly negative electron affinities, so they typically form anions in natural conditions. You will not find elemental fluorine, chlorine, bromine, and iodine anywhere on Earth. I won't say anywhere in the universe because I haven't been everywhere, but anywhere on Earth, I haven't been everywhere on Earth either, but trust me, you won't find these in their elemental form unless you go to a chemistry lab or some sort of place where they have that. Let's see. They react directly with metals to form metal hydrides. So, sodium chloride is our sort of prototypical salt that we think of. You'll see the ionization energies are fairly high here, so it's difficult to form cations with these, But anions, because of their electron affinities, anions are pretty easy to form. It is the only group that has a solid, liquid, and gas all in the same column. And I'll show that to you here by looking at the table. Hopefully you've seen this, that the red letters are gases, the blue ones are liquids, and the black ones are solids. These down here were supposed to be purple. They just didn't turn out very well on my printer. But so those two are liquids. These just don't form. They don't form. They don't form. We don't know if they're metals, liquid, or metals, nonmetals. I'm sorry, we don't know if they're liquids, solids, or gases there. So they are unknown. Probably most of them are metals, but most of them are solids, but we may have a gas or a liquid over here. These don't last very long. So, all right. So it's the only one that has a solid, liquid, and gas all in the same group at 25 degrees Celsius. They are highly reactive. So halogen has very high reactivity, and we've got pictures of them over here on the right. I don't have fluorine. I don't have a picture with fluorine, and I'll explain why that is here in a second. Fluorine is the most reactive element on the whole periodic table. It's the meanest, baddest, most electronegative element on the whole periodic table. Fluorine will mess up your day. Just trust me on this. Fluorine's really, really, really reactive. In fact, you'll notice that here we've got chlorine, bromine, and iodine in some glass ampules. If you take fluorine and put it into a glass ampule, the fluorine will react with the silicon in the glass, and it will etch its way through the glass. It will eat through the glass because fluorine is really, really reactive. All right, fluorine has a pale yellow color to it. There's special equipment you have to use if you're going to be doing fluorine gas chemistry. If you take fluorine, if you take your arm and stick it into a stream of fluorine that's coming out of like a tank, your arm will catch on fire. Yes, fluorine is very reactive. Chlorine, not as reactive, but still pretty darn reactive. It is a gas, and it has a greenish yellow color to it. You can just barely see a yellow tint to the gas here because it's not very concentrated in there, but there is a yellow color to it, and it's kind of an irritating odor. If you've ever been to the pool and somebody just chlorinated it and it has that very strong chlorine smell, well, then you know what chlorine smells like. All right, bromine is less reactive than chlorine, but it is still quite reactive. It is a liquid at room temperature, so here's the liquid, but it does have a significant vapor pressure, so you'll see there's quite a bit of gaseous bromine above that liquid. So pretty nasty stuff. You probably don't want to have a glass ampule of that around the house. And then here is iodine. Iodine is a black solid. So it's a steely looking solid, black and kind of shiny. If you shine light on it, you'll see that it kind of reflects back some light. When it gets into the gas phase, it has a really cool purple color, but it smells horrible. It can make you, it feels uncomfortable to breathe it. So anyway, that's iodine. So solid, liquid, gas, all in the same group. Group 8A, the noble gases. All right, this is our final group. We're almost to the end of the chapter here. They have very large ionization energy, so you'll see the numbers here are quite large, although they're approachable when you get down here to the bottom. And I'll talk about that, how that's important here in a minute. The electron affinities are positive, so since the electron affinities are positive, they can't form anions. So they just don't ever form anions. And since their ionization energies are so large, they don't really form cations either. So you will never see a noble gas in an ionic compound. If you do, let me know, because I'll be surprised. They are very, very unreactive. So they are very, very unreactive. They just don't, they just don't do anything. They are found as monatomic gases. And on the next page, I'm going to show you some pictures of these. But first, you'll see these all have 8 outer shell electrons. So they have full octets, except for helium. But helium is only going to have 2 anyway. So boiling points, they do increase as you go up. But these are all gases at room temperature. Densities, these are all in grams per liter, but that's still all pretty low. And then over here, ionization energies are pretty big. And then finally, here it is possible, but very rare, to make compounds with noble gases. But to do it, you need something really, really reactive, like fluorine, right? So something really, really reactive. So there are 3 known compounds. There may be another one in there somewhere, but xenon, I know for sure, makes these 3 compounds: xenon difluoride, xenon tetrafluoride, and xenon hexafluoride. The tetrafluoride is listed over here. And in our next chapter, when we're talking about Lewis structures, you're going to see what the Lewis structure of this is, and it's kind of cool looking. All right. Krypton forms only one stable compound, krypton difluoride. Argon forms only one compound, HARF, and it's only stable at very low temperatures. And so you will find that the reactivity does increase as you go down to the extent that it has any reactivity. Xenon is more reactive than krypton, but that just means it forms 3 compounds instead of just one. And argon is not very reactive. It forms 1 compound, but only at really, really low temperatures. If you heat it up to room temperature, it just decomposes into HF and argon gas. So, okay, so now that we've looked at that, I want to mention something about these ionization energies. Because the elements down here have low ionization energies, it's possible to make compounds with them. Now, you don't fully ionize them, so you don't really make cations of them. But because they have those relatively low ionization energies, that's why it's possible to make compounds with xenon and krypton, and to the lesser extent, argon. But you will never, ever make a compound with neon or helium. Again, if you do, let me know. I want to see that, but it's not going to happen. All right, we're going to look at 64, and 64 kind of looks unrelated to what we just talked about because it's kind of unrelated to what we just talked about. But it is important, so I'm going to show you how to do number 64. And by the way, this is our last problem. Oh, wow, this video is getting kind of long, but hopefully eCampus will accept it. All right, so write balanced equations for the following reaction. We're going to react potassium oxide with water. So potassium oxide is K2O, and we'll call that a solid. We're going to react that with H2O liquid. Well, if you have a metal oxide and you react it with water, you are going to get that same metal hydroxide. So potassium's +1, so you're going to get KOH. And that's it. So if you have potassium oxide plus water, you'll get potassium hydroxide. Any metal oxide plus water should give you the metal hydroxide, and that will be AQ. Now, we do need to balance it. I think that takes care of it. Let me look real quick. That does take care of it, so that will be the reaction. All right, so since we just did a metal oxide, let's do another one. Here's calcium oxide. So calcium oxide, solid, and then H2O, liquid. So an oxide, a metal oxide plus water is going to give you the metal hydroxide. So calcium form is a +2 charge, so you'll have calcium hydroxide. All right, and if we look, calcium's balanced. We've got 2 oxygens on each side, 2 hydrogens. So that's already a balanced equation, so we're good there. Now, for nonmetal oxides, when they react with water, they will form oxyacids. So for nonmetal oxides, when they react with water, they will form oxyacids. To figure out what the oxyacid is, then you really need to look at the oxidation state. So let's go ahead and go through this. Diphosphorus trioxide, so that's P2O3, and that's a solid. And we're going to react that with water. So we don't know for sure. We don't know, I do because I've done this before, but we don't know for sure which compound, which oxyacid this is going to form. So let's look at the possible oxyacids that we could form with phosphorus. Well, the ones that we know for sure are H3PO4, which is phosphoric acid, and H3PO3, which is phosphorus acid. And so now we're going to look at the oxidation states. And whatever the oxidation state for this is, that's also got to be the oxidation state for the oxy acid. So, oxygen is -2, -2 times 3 is -6. That adds up to has to add up to 0 because it's a neutral compound. So -2 times 3 is -6, and so this has to be +6 divided by 2 gives us +3. So the phosphorus has a +3 oxidation state. So now let's come over here and look. Again, total thing here is 0. -2 for oxygen. -2 times 4 is -8. Hydrogen is +1. +1 times 3 is +3. If you're thinking, I don't remember how to do this, go back to chapter 4. I had a bonus lecture that was oxidation states, names and oxidation states. +3 plus -8 plus some number gives us 0. That has to be +5. So the oxidation state of phosphorus is +5. So it's not phosphoric acid. For phosphorus acid, we have -2. -2 times 3 is -6. Again, that all adds up to 0 because it's neutral. +1 for the hydrogen times 3 is +3. So +3, -6, and some number gives us 0. That's +3. Divide by 1, +3. So oxidation state of phosphorus here is +3. So that means that the compound here is going to be H3PO3 AQ. And that's supposed to be a 3 there, but all right, that's a 3. There we go, H3PO3. All right, if we look, this is not quite balanced. Let's see, I'm going to lock that in place. So we've got 2 phosphorus there. We'll put a 2 there. And then let's do hydrogen. We've got 2 times 3, that's 6. So we'll put a 3 here. And now let's count the oxygen. 3 plus 3 is 6. 2 times 3 is 6. Okay, so that's it. That is our balanced equation. Again, you just need to match up the oxidation state. Let's look at dinitrogen pentoxide. So N2O5 solid plus H2O liquid. All right, if we look at the oxy acids with nitrogen, we have HNO3, which is phosphoric acid, and HNO2, which is, HNO3, which is nitric acid, and HNO2, which is nitrous acid. I said the wrong word there. All right, let's figure out oxidation state. So it's -2 for the oxygen, +5 for nitrogen. We don't need to figure out for water. So we come over here, and we look at the HNO3, -2. -2 times 3 is -6. +1 for the hydrogen times 1 is +1. So that's +5. It's a +5 oxidation state. So that means nitric acid is our acid here, HNO3. All right, now to balance this, we've got 2 nitrogens here, only 1 there. So we're going to lock the 2 in place, put a 2 there. And now let's look at hydrogen. We've got 2 hydrogens there. We've got 2 there, so I'll put a 1 there. And then we have 5 plus 1, that's 6 oxygens. 2 times 3 is 6 oxygens. So that is it. Okay, so there are others. These non-metal oxides that form acids, these are called acid anhydrides. So acid anhydrides. A couple of the other interesting ones are SO3. When you add H2O to it, you'll get H2SO4. And if you have SO2 plus H2O, you will get H2SO3. Okay, CO2 plus H2O will give you carbonic acid, H2CO3. I'm trying to think of some other ones here. Like chlorine, there's a whole bunch of them. So Cl2O5 plus H2O, and it'll give you HClO3. You'll see the oxidation state is +5 there, and that's supposed to be a chlorine there. So HClO3 to, I think that comes out. Anyway, so those are just a few examples of some acid anhydrides that get turned into acids when you add water to them. Kind of interesting. All right, well, we've gone way over an hour. We're an hour 34 minutes. Hopefully this will upload to eCampus just fine. But that is the end of chapter 7 here. I always like to do this, my favorite page in every chapter. All right, slideshow is over. And look forward to chapter 8.